Hello. Today we will talk about Lagrange multipliers. Lagrange multipliers. In particular, we will like to do an example based on that, and we'll take a very simple example, the simple pendulum. Right. So let's, before we proceed on to actually use Lagrange multipliers or even introduce Lagrange multipliers, let's review the idea of a simple pendulum using Newtonian mechanics. So let's say, so simple pendulum using Newton's laws. Let's review that. So simple pendulum deals with, let's use some lines here. So that's and that's a mass m. Let's introduce some variables here. Let us just for concreteness, we will say that's our y hat direction, that's our x hat direction. We'll measure quantities in the counterclockwise direction, and this angle will be said to be angle phi. We will also find it convenient to introduce the vectors r hat, which is radially outward, and the vector phi hat, which is perpendicular to that in the direction of increasing phi. We'll fix the length L of this pendulum fixed, and we know that this is going to go along a circle of fixed radius, that is the length r. What are the forces acting on this mass m? There are two forces. One is the force due to gravity, that's mg, and the other is the force due to the tension T in the rope or in the rod, right? So it's a tension T. So Newton's law tells us that mass times acceleration of the bob is equal to the sum of, or the vector sum of, all the forces acting on the mass m. And there are two forces acting, so we have mg plus the force of tension. That's Newton's law. Since we would like to work in a specific coordinate system, we would like to, instead of working in xy coordinates, let's work in r and phi hat coordinates. For that purpose, let's remind ourselves of what acceleration is in those directions. So let's go back and remind ourselves. So we call this acceleration in r hat and phi hat coordinates. I shouldn't say r hat and phi hat. I think it's more appropriate to say it is r and phi coordinates. In r and phi coordinates. For to that end, we begin by saying that the vector r, the position vector r, will be the radius r times r hat, right? That's the definition of the position vector. Velocity v is dr by dt. That's equal to, we distribute the derivative in both the magnitude and the vector. So we get r dot times r hat, or it could be the other way. It could be r times r hat dot, right? And we realize that r hat dot actually is it's a change in the vector r hat. The change in the vector r hat is in the direction of phi hat, and it turns out that is phi hat times times phi hat. So the velocity v is r dot times r hat plus r phi hat times r rate of change of phi times phi hat. Similarly, acceleration is a derivative of velocity now, and we have to proceed and take the derivative of all 5 terms in here. So this leads to r double dot times r dot, but then now you can take the derivative of r hat. That's plus r dot. R hat we said is phi hat phi hat times hat. And next, there are 3 terms more. So this is r dot, phi dot times phi hat. That's coming from the derivative of this r term in here. Next, we take the derivative of phi dot. So this is r phi double dot times phi hat. And finally, we can take the derivative of phi hat. So this is phi hat dot. We remind ourselves that that's equal to rate of change of phi comes into picture, and it is in the direction of minus r hat. So this is phi hat times minus r hat. Right? I've not completely emphasized on or illustrated this, but that's I presume that you've come across this before somewhere else. That's minus r 5 dot square now, because there's a phi dot from here and there's already a phi dot there, and that's all right. Now that leads to if I were to collect all the r dot terms together, I have r double dot minus r phi dot square times r hat plus 2 times r dot phi dot plus r times phi double dot times phi hat. And there are interpretations for each term. The first term here, r double dot, is the radial acceleration. The second term is the centripetal acceleration, that is radially inward. The third term is a Coriolis force that depends on both the rate at which r is changing and the rate at which phi is changing. And the last term is actually the tangential acceleration, which purely depends on the second derivative of phi. For our purposes, we have r is fixed, r is equal to L, which is fixed. That means r dot is 0, right? R dot is equal to 0. In that case, we have simplifications. We have the position vector r is simply L times r hat. The velocity v is, since r dot is 0, so it is simply L times phi dot times phi hat. So it is completely tangential. It's completely in the tangential direction. And the acceleration A, double dot is 0, so there is a centripetal acceleration still. So this is L times phi dot square in the r hat direction. And since r dot is 0, the Coriolis force doesn't exist, but there is still a tangential acceleration in the tangential direction. So it's L times phi double dot times phi hat. So all the dynamics is because of the change in angle. That is what this means. So this is how we would proceed using Newton's law. So that's good. So let's go now and substitute this back in 1, right? So we'll use the acceleration term in equation 3 and substitute it back in 1, right? The Newton's law. So let's see. So using 3 in 1, 3 in 1, we have what was mass times acceleration. So it is mass times, let me see, where we go back. So it is L phi dot square. So it is minus L phi dot square. That's a centripetal acceleration in the r hat direction, plus L times phi double dot, right? That's a tangential acceleration if you want, and that's in the phi hat direction. That's mass times acceleration. That's equal to mg, can be broken into r and phi dot direction as mg cosine phi in the r hat direction, plus is actually minus mg sine phi in the phi hat direction, correct? And that's because we have mg here like this, and that's your r hat, and that's your phi hat, and that's angle phi. So it's mg cosine phi in the r hat, and it is minus mg because phi hat is in the increasing phi direction. And finally, there's tension force, which is radially, but it is radially inward, so it is minus the tension force in the r hat direction. That's your Newton's law broken into your unit vectors r and phi. Now we can collect them together in the radial and phi direction. So suppose I were to take the dot product of this equation with unit vector r, so the components of the forces in the direction of r hat, we say is equal to the centripetal force, that's ml phi dot square is equal to mg sine phi and minus t. And in the direction of phi hat, we have ml phi double dot, that's the tangential acceleration, that's equal to minus mg sine phi. That's the two information. So, so this seems to suggest that, or maybe I should point out what here are some interpretations. So the phi hat direction, if I were to cancel out the mass m, divide out by L, what we have is phi double dot is equal to minus g over L times sine phi. That's your equation of motion. That's the equation of motion. Or that means to say that this is what deals with the dynamics. It quotes the motion as, or motion is all about change in phi in this case. But what about r hat? We know that there is no motion in the direction of r hat in this particular problem. In general, we will have a motion in the r hat direction, but for a simple pendulum, the pendulum is constrained to move with r equal to L, and that leads to a balancing act, if you want, which is pretty much governed by the tension T. The tension T uh, is conspiring to make sure that Newton's law is obeyed in the r hat direction, and that's given by cosine phi plus ml phi dot square. So notice gravitational force exists in the radial direction, but there is also a centripetal which we would say is a pseudo force in the way we are interpreting here. But together, these two forces, they have to be balanced by the force of tension, and if there is sufficient tension in the string, this will be satisfied, and this is the equation of constraint, if you want. There is no information about motion here, so this is equation of constraint. This makes sure that Newton's law is satisfied in the r hat direction. And that's the two information. And we would like to have these two information from the Lagrangian concept also. And as we have seen, we will try to highlight that in the generic, in the Euler-Lagrangian way of proceeding, we only get the equation of motion, and the equation of constraint is, even though used in the relation, it doesn't show up in the form we have written, or the force of tension doesn't show up immediately in the Lagrangian formalism. And that's where the idea of Lagrange multipliers comes, and we will try to point out how we can actually decipher this force of tension out of the Lagrangian formalism. So to this end, let's proceed, and let us say that we construct the Lagrangian for this system. So let's go to a new page at this stage. So this is equation, so article 6, item 6, let's say, and we say Lagrangian for a simple pendulum. So the Lagrangian is equal to, it's given in terms of, we know in this case, as everything, or let me proceed the way one would in general. So there's a vector, it depends on vector r and the velocity v. Right? Just to clarify, the vector r here is x in the x hat direction plus y in the y hat direction, or x in the I direction and y in the j direction. Remember, y is vertically upward. So that's equal to half mv square, the kinetic energy, minus the potential energy, which is mg times the vertical height. The vertical height is uh, is downward, so this is minus mgy actually, right? So this is how far you are. So this is velocity square is, we immediately realize that this is x dot square plus y dot square minus mgy. That is how you will begin writing the Lagrangian. But then the uh, whole theme in the Lagrangian formalism is to identify the constraint and to choose the right generalized coordinate. So we look for the equation of constraint. So equation of constraint now. So there is a constraint, and the constraint is that the pendulum has to be on a circle of radius L. So that's your constraint. Immediately we realize that this is that's an equation of a circle, but just to proceed in a differential manner. So we take the differential of this equation, and we learn that this is x dx plus 2 times y dy, and there is no change in L, so that's equal to 0. If I were to divide it out by a small length, a small time dt, I learn that x dot is equal to minus y dot. Right. Right. That's another form of writing the equation of constraint, but we would prefer x square plus y square is equal to L square itself. We know that if things are constrained on a circle, we have x is equal to L cosine phi in terms of the variable phi introduced in the diagram on the first in the first page, and y is equal to L sine phi. No, is minus L sine phi. Oh no, x is L sine phi, sorry. So x is L sine phi in our diagram, and y is minus L cosine phi, which implies that x dot is equal to L cosine phi times phi dot, because L is a constant, and this implies that y dot is equal to L sine phi phi dot. Right. That's the equation of constraint, and we immediately get the Lagrangian in terms of this. we can replace x dot square plus y dot square. It turns out to be L square phi dot square, then using the x dot and y dot relations coming out of the constraint. And we learned that everything depends only on the angle phi. Phi is the important parameter. That's a generalized coordinate. The motion happens in terms of phi, or the mass m is completely characterized by angle phi. That's the understanding. And the Lagrangian takes the form m L square phi dot square minus y is minus L cosine phi, so it changes sign, so it is minus mg L cosine phi. So everything depends only on phi. Immediately we find our Euler-Lagrange, to use our Euler-Lagrange equation. We find the generalized momentum, which is the change in Lagrangian with respect to the phi dot, and that's m L square phi dot. That's the angular momentum, if you want, and the change in the Lagrangian with respect to the angle phi, which will be the torque, is equal to minus mg L sine phi. And the equation, Euler-Lagrange equation, tells that time derivative of the generalized momentum should be equal to the torque. So that tells us that m L square phi double dot has to be equal to minus mg L sine phi, which is, of course, the equation that we already saw using Newton's law. Like, no surprise, this is what Lagrangian is all about, right? But what about tension? Right? What about the radial forces? So this is correct. This is perfectly fine. This is the tangential forces leading to the dynamics of the mass m. But what about tension? About force of tension? That's also an information. It seems like that's a nice insight we have using Newton's law. But can we say anything about the force of tension using the Lagrangian formalism? And that's what Lagrange multipliers is about. So to this end, let's go back and write a new Lagrangian this time. So let me go to a new page. So again, Lagrangian is, we wrote this earlier, this is equal to half mv square. So let me write that as v dotted v with v, nothing different. That's just, I chose to write it like this time. And minus mgh, let me write that as minus mg vector g dotted with vector r. Remember, this is your mg, it's your vector g, and that's your vector r, or hat, if you want, and that's angle phi. Right, so mgh actually is mg L sine phi, right, or cosine phi. So that's mg L cosine phi, but L cosine phi this also is equal to mg dotted with vector r. remember vector r is equal to L times r hat. Right? So that's just writing the same whatever we have known in terms of vectors, just to see this slightly, have an insight of what's going on. Now, now we change this Lagrangian, right? And not significantly, but conceptually relevant. But we are going to add a 0 to this Lagrangian. Why not? Right? You can always add a 0. So it's mg dotted with vector r and plus I introduce what is called a Lagrange multiplier and do the following: r dotted with r minus L squared. So this is the Lagrange multiplier. It's an arbitrary multiplier at this point. So this is arbitrary Lagrange multiplier. And remember, r dotted with r minus L square is the equation of constraint. R dotted r minus L square is actually x square plus y square minus L square. That's the equation of a circle. That's an equation of a constraint. That's equal to 0, right? That's our constraint, right? That's our constraint. So what have I done? We started with the old Lagrangian, but now added so-called innocent looking term, added a 0 basically with a arbitrary Lagrange multiplier to it. Sounds it should be all okay. And with this, now let's again work out our Lagrange Euler-Lagrange equation. But this time we have both the coordinates in, right? We're not really using the equation of constraint the way we proceed in the Lagrangian formalism. So let's see. So the momentum equation is dl by dv, right? In complete form, in the sense that both components are there. The complete vector is in there. I'm not just working in the in the tangential direction. Both the radial and tangential direction are in there. That's equal to mass times velocity. Right? So it's only one term that has velocity in it. So it's mass times velocity. And L by dr now, right? That's your generalized force. This is generalized momentum. Momentum is the same. Generalized force now gets two terms. Earlier it would have got the contribution only from the gravitational potential energy, but this time it gets a contribution from the constraint term that has been introduced as Lagrange multiplier. So the generalized force now is minus mg right. Oh, I have to check the equation mg dotted with r, right? Did I do this correct? Mg g vector g dotted with r is in the negative direction, so mgh actually is minus mgl cosine phi, correct? So this is minus mgr, so this should be plus. So I changed my potential energy here, right? So this should be plus, right? That's what we expect the force acting is mass times gravity. The error is basically because we tend to put the direction or doubling the direction is encoded in the vector itself. But the new part here is that there is a force getting a contribution because of the constraint, and that is equal to plus lambda times, I have to take the derivative with respect to vector r, so that's lambda times r, vector r, right? And our Euler-Lagrange equation using this takes the form, so time derivative of the momentum, which is acceleration, so remember d by dt dl by v is equal to mass times acceleration. Right? And Euler-Lagrange equation is pretty much so by dt dl. So time derivative of the generalized momentum is equal to generalized force, right? This implies the Euler-Lagrange equation tells us that mass times acceleration is equal to mg plus lambda times vector r. Okay. That's what we learn from from the formalism of Lagrange multipliers. But now compare this with the Newton's law, all the way the first equation that we wrote down, mass times acceleration is equal to the sum of the two forces. So it seems like the Lagrange multiplier lambda term somehow fix the force of tension. Right? So let me add, so comparing one and 11, we learn that force of tension is equal to lambda times vector r. Force of tension, we said, is minus t in the direction of r hat, and this is lambda times the vector r here is L times r hat. So we learn T is equal to minus lambda times L. Thus it seems like the suggestion is that the Lagrange multiplier is the force of tension Remember, force of tension is what makes something constrained, right? Force of constraint is a constraint force, constraint that constrains the mass along the constraint, if you want. It's a dummy statement in a sense. Is a force, thus Lagrange multiplier is a force of tension up to a scaling factor minus L, right? It was, I could have subtracted the Lagrange multiplier term and plus or minus, so it cannot really pick the direction of the tension for you, but it tells you that it is the force of tension or the Lagrange multiplier lambda is actually conspiring to create the force of tension so that it actually achieves the constraint. This hopefully helps you to or give some insight on how the constraints are captured in the Lagrangian formalism. We'll do more examples. In the future. We will do so. For other examples, one can do. We can talk about a rolling wheel. There is force of friction acting on it. One should always. It's an interesting thought process as to if you have a wheel on a horizontal surface, for example, the wheels of your car, and ask what's the direction of friction acting on these wheels? Is it in the forward direction or is it in the backward direction? And as a hint, just to make you guys think, I would say it's different and on different wheels of the car. So that's one thing we will do. Second is gears, the same idea stretched out. It's gears. So by gear, I mean, so you could have two wheels in contact with each other. One is smaller and the other is, and they're rotating with respect to each other just because of the friction between them. We ask what is the relative motion. And the third is Atwoods Machine. That's also a nice example of constraint motion. So it's machine. And of course, almost every other problem in Lagrangian mechanics can be worked out this way, but these are some of the few that's very has an illustrative feature in this. And actually, fourth one is spherical pendulum. That's a nice, rich problem in this constraint. Hopefully, I'll be able to put in more videos on this, but for now, let me stop. And how do I stop? Yes, okay. And thank you for listening, and hope to be able to record more examples. Bye-bye.